Hi, everyone. My name is Annika, and I work on collaborative visual intelligence, which is one of the key pieces that will enable multi-robot systems to work together. Here's the clicker. We're going to be seeing a lot of teams of robots working together in the next few years. We're going to be seeing robots in warehouse settings, packing boxes, alleviating some of those physical stresses on our factory workers, and handling logistical details in real time. We're also going to be seeing them in more industrial settings, hopefully helping us out with our chores. We're going to be seeing multi-agent teams in settings like search and rescue, and helping with natural disaster scenarios. We'll be mapping these scenes in real time in order to help us allocate resources efficiently. In one of my favorite applications, we're going to be seeing multi-robot teams on the moon and on other planets. They're going to be going places that humans can't go in these extreme environments, intelligently figuring out how to map, how to collect samples. So why don't we have these yet? Why don't we have these multi-robot teams working in these different scenarios yet? Well, collaborative robotics is a pretty big puzzle. There are a lot of different pieces to it. But one of the key pieces is happening under the surface in the brains of our robots. And that's where my research happens. A lot of our robots are programmed in order to carry out their tasks individually. They basically ignore other robots. They make their own map of the world, carry out their own tasks. But in my research, I want our robots to learn from one another, to be interested in what the other robots learn in order to kind of create this collective hive mind about different scenarios. And in order to do that, our robots have to learn how to intelligently understand the world and see the world, and they also have to think collectively in order to collaborate. So how do our robots see? Well, take that natural disaster scenario, for example. We have robots that are flying over dense forested regions, and they have to learn how to localize. So what we do in one of my most recent projects is we use spatial AI in order to extract the objects from the scene. In this case, these are the location of trees in the scene, and then we create this kind of geometric map of where all the objects are. And when we represent the world in this fashion, we're teaching our robots how to create this kind of geometric map that can be understood when the environment begins to look very different. So we can localize drones in the same place. They're creating maps that look the same across all of these different seasons. And this is one of the major challenges of collaborative robotics, is teaching our robots how to create map representations that they can share and understand when the environment begins to look different. So we've also expanded this type of approach to ground-based robots as well. In this case, we have two different robots, rovers, that are driving around in this unstructured setting. And this is a pretty challenging setting because as our rovers approach places from different angles, from different viewpoints, the images begin to look pretty different. This is the same spot kind of coming at it from two different sides. But as you can see in the bottom, when we begin to make this geometric map of all of the objects in the scene, this is something our robots can use to talk to each other, to share information with one another. And we're actually also embedding language in this scene so that our robots can share that important information that might be dependent to the task at hand. So with these representations, we're teaching our robots how to talk to one another, how to share their maps and understand one another's maps. But what if we want a human in the loop? What if you or I also want to understand what the robot is making without having to get a master's or PhD in robotics? So if we want a human in the loop, we've kind of got a lot of different approaches. The state of the art for the last 10 years or so has been creating these feature or point-based maps. You can see in the bottom left, we're mapping a desk here. And these point clouds are kind of like the IIA instructions of mapping. If you squint, you can kind of begin to see where things should go, but it's still pretty difficult for you or I to understand. If we colorize these points, it begins to get a bit more understandable, something that we can actually wrap our heads around. But this map still doesn't really have any substance to it. Our robots can't use it to navigate or really share information. So in the last 5 years or so, researchers in robotics started using what are called voxels. So you're probably familiar with pixels. Those are 2D squares. Voxels are 3D squares. So we're now representing the environment as kind of these cubes, and we can select different granularities of them. The issue with this is, again, it's still not super easy for you or I to understand. You can kind of see the desk in the middle of that voxel-based map on the right there, but there's not a lot of information for a human in the loop. Then about 5 years ago, we had a paradigm shift in the world of 3D reconstruction when neural radiance fields came out. These came out, and we were able to create these 3D reconstructions of environments that are things that you and I are pre-programmed to understand, because this is how we experience the world. The only problem is when you try and put this on board a robot and render this in real time, you might melt your GPU. So in the last couple years, we've seen another shift when this new technology came out called Gaussian splatting. And this is something that can run on board in real time. We can render these images in real time. And this is where I'm doing my research. We are creating environment representations. We're embedding information in the scenes, like language, in order for you and I to be able to understand this. And one of the coolest things about Gaussian splatting is this can be rendered in real time. This is something that we can move through the space and understand and render without having to use a massive GPU. So what I'm doing in my research right now is we're expanding these representations beyond these small-scale indoor settings to large outdoor environments, like here on MIT's campus. And if we slightly reduce the fidelity of these maps, over the course of even 50 frames of movement, we're able to create these 3D reconstructions that you and I can understand in real time. And the next steps for our research is taking this into the collaborative setting. We're actually building these maps with multiple different robots, and we're fusing them together so we can send out a team of agents into a large space and create a 3D reconstruction. So if I can leave you with anything here, when it comes to the multi-agent problem, one of the key pieces is this collaborative spatial intelligence and understanding of the environment. And in order for our robots to work together, they first need to learn to see together. Thank you.